Continue. All right, now let's continue with part 2, where I talk about causality. Causality for machine learning and machine learning for causality. Who of you has been to Sarah's module about causality? If you, okay, good. This is not a prerequisite in any way, but you may correct me if I say something stupid. I will talk about 3 things, and I'll try to keep everything short. I'll talk about why I care about causality in a company that cares about deep learning and edge devices and chips. I will talk about machine learning for causality in an example of how we can learn both causal variables and causal structure from pixel level non-IID data. And finally, I will talk about an example of causality for machine learning, about how we can use ideas from causality to solve problems in imitation learning. Now, why causality? What is causality? I think it makes sense to describe causality in 2 different ways. On a semantic level, on a descriptive level, causal models describe relations between variables. But in addition to just describing the probability distribution between variables, they also add a descriptive layer that says that some variables are the cause of other variables. So there's an additional description of relations between variables as that of cause and effect. So in a causal model, there's a difference between saying the number of hours that the sun is shining a day causes the amount of ice cream bought at Massimo Gelato, and saying the number of the amount of ice cream bought at Massimo Gelato causes the number of sun hours a day that we record. Even if this difference isn't obvious from a probability distribution, there you just see that the 2 things are correlated. Now, the second level of causality is a functional level. Causal models do not just describe a single probability distribution, but they allow us to describe how a probability distribution changes under certain changing conditions. To give you one particular example, in this ice cream at Massimo Gelato and sun hour situation, in a causal model, we could ask the question, if I force Christos here in a randomized control trial to eat ice cream every single day, independent of the weather, would that make the sun come out in the winter? And I'm not sure if this works in Amsterdam because we're eating ice cream no matter what. But in a causal model, you can answer these questions, right? And if ice cream consumption causes sun hours, then the answer is yes. If sun hours causes ice cream consumption, then the answer is there is no difference. So there's this kind of meta model of probability distributions that you get. You can talk about these different distributions. You can just observe how much ice cream is eaten and how much the sun shines, and you can perform experiments where you kind of change some of these components. So if you squint a little bit, if you take a step back and don't look at the details too much, then I think you could say causality is a language to reason about certain kind of changes. And I think this is really the essence of causal models that also helps you to see when this kind of stuff can be useful. In a more formal level, causal models can be described in different ways. There's graphical causal models or causal graphical models or Bayesian causal models or causal Bayesian models. And there are structural causal models. And today I want to talk a little bit about structural causal models, but not too much to not bore you. So a structural causal model consists of a set of causal variables. This is the ice cream consumption and the sun hours. And then a set of noise variables, just random variables, for instance, following some Gaussian distribution, and then a number of mechanisms, which are functions that map the noise variables to the causal variables. And now one important thing is that if a variable has causes, so if it's the effect of something else, then the causal mechanism, this function f, will also depend on the value of the causes or the causal parents in the causal graph. Right? So in the sun and ice cream example, the sun hours don't have a causal parent, so it's just the Z1 could be the hours the sun are shining, and this is just described as a function of some noise variable, just as a pretty random effect. And then Z2 could be the number of ice cream cones eaten at Massimo, and this now depends on whether the sun is shining or not. Then the second concept I want to talk about is that of a solution. The solution function is the combination of all of these mechanisms into one function that maps all the noise variables, so a high-dimensional vector of noise variables, to all the causal variables, so some vector of quantities you may be interested in. And we can construct this by just combining all these causal mechanisms. It doesn't really matter so much how you do it in practice. But once you have this, you can take the distribution you have for the noise variables, push it through the solution function, and get a distribution over the causal variables. So this is the distribution of all your causal variables together. From this, you can see the correlation between ice cream consumption and sun hours, for instance. So far, this is nice. So far, nothing new. But now the new thing in causal models over non-causal models is that we can also change out these mechanisms. We can say we perform this experiment where ice cream consumption no longer depends on sun hours, but instead we force somebody to eat ice cream, or we forbid them to eat ice cream for some reason. You get new mechanisms, you switch them out, and then because you have this new mechanism, you get a new solution function, and then ultimately you also get a new distribution of the causal variables. So in this sense, the formalism allows you to get not just an observational distribution, just kind of observing what the causal variables do if you monitor humanity or whatever your system is, but you also can reason about, hey, I changed this one mechanism, now I get a new distribution. This was very quick, and I hope that Sarah spent more time on this stuff, but maybe for now this is enough, and I will come back to a few of these things later, but they will not be super crucial to take something away from this talk, I hope. Okay, now, there's two ways in which causality and machine learning can come together, I think. One way is that we can use machine learning to answer causal questions. We can use deep learning or whatever you have to write algorithms that try to find a causal model of the world around us. One example of this is causal inference or causal discovery. So this is the problem where you have a data set, a tabular data set of causal variables. For instance, patients in a hospital where the data sets consist of, I don't know, have they read Harry Potter in their youth? Are they smoking? Do they get cancer? Something like this. And then you can ask the question, how are these variables causally related? But you already have the causal variables. You just need to find the structure between them, or the graph and the mechanisms in these SCMs. So you could ask questions like, does reading Harry Potter prevent you from smoking? Or you could ask the question, does reading Harry Potter give you cancer later in life? These kind of questions are answered in causal inference or causal discovery. The second type of problem you could be interested in is causal representation learning. It's kind of the same. You still want to learn causal relations, but you don't know the variables. You just have some low-level unstructured representation of the scene. Say, from the camera in your room, you take a picture of all the people in it. Now you want to know something about the dynamics of the people, but you just have raw pixels. Maybe a better example is traffic. You have an autonomous vehicle that just records the world through a bunch of cameras, but you want to figure out that the important causal variables are maybe the speed of other cars and maybe the aggressiveness of a driver, maybe whether a traffic light is red or green. So you kind of need to infer these things from the pixels first and then find the causal relation between them. And this is also important for robotics, for instance. And why would you care about any of this? Why do you care about causal models of the world? One reason is science. Sometimes we just care about causal structure as an end goal in itself. We want to understand what causes what. We want to write papers about how weird behaviors in biology cause other weird behaviors in biology, whatever. Sometimes it's about planning. We want to know, we want to satisfy some end goal, like people not have cancer. And then we want to find which interventions, which shifts in the mechanisms we need to perform to achieve this, make them read Harry Potter. And finally, it has been speculated that causal models are more robust under domain shift. So if you have a system in two environments, it's simulation and the real world, some people believe that if you describe the system in a causal way, factorize it with these mechanisms, that you train your system on simulated data and transfer to the real world, it is more robust to this change because just some mechanism change, something known as the sparse mechanism shift hypothesis. But this last thing is really speculative and hasn't really been convincingly demonstrated in any reasonably realistic setting yet. Okay, this is the first class of machine learning and causality. Learn causal models of the world. The second kind of application is causality for machine learning. And here the idea is that you have some machine learning problem that you just want to solve, and you want to use some causal understanding of the learning process itself, how the data and the model interact with each other, or maybe how an agent in reinforcement learning interacts with this environment to improve your machine learning algorithm. And I show you one example at the end of my part of this lecture from imitation learning, but yeah, maybe I'll skip over this a little bit right now. But these kind of causality-aware learning algorithms can be useful when naive learning algorithms fail, and naive learning algorithms even fail in the limit of infinite data in perfect optimization. And yeah, you'll see an example of this in a bit. But sometimes understanding causal structure can be really useful to find your fundamental problems in machine learning. Good. This was my introduction. Does anybody have questions at this point? Excellent, because I'm a little bit behind time. So I will now talk about two examples of these things. I will talk about machine learning for causality, and then I'll talk about causality for machine learning, time permitting. Let me start with machine learning for causality. Yeah, this is at least not so pixelated. If you've seen a scene like this, I assume you're all human. You're probably not thinking, hey, this is a nice collection of pixels, and this is a nice correlation patterns between the color waves that the pixels take on. Rather, you're probably intuitively grasping this as a robotic finger or robotic arm interacting with a couple of buttons that somehow light up when you touch them on a table. And if you look very closely and the light wouldn't be a little bit bad in here, you'd also see that when you touch the green button, for some reason, the red button also goes on. You could also have a different causal model. You could also think that somebody's sitting under the table, and whenever they turn on a button, they also pull out a magnet and draw the arm closer to it. But probably with this very intuitive understanding of the scene, both in terms of high-level variables, like the position of a robotic finger, and causal structure. The robotic finger causes the lights to go on when it touches the buttons. Machine learning systems, most of them are different. They're just really, if you train a VE or diffusion model or something on a scene like this, it will really just pass this on the level of pixels and the correlation patterns between the pixels. And there's no notion of these high-level concepts really in there. In this work that I'm talking about now, we kind of want to bridge this gap a little bit. We want to answer the question if it's possible to learn causal variables and the structure between these high-level causal variables from pixel-level data, and ideally without labels in the training. And I'm talking about this now to you because we found that this is indeed possible in a particular weakly supervised setting from non-IID data. And then also we'll show you how we can turn this into a practical algorithm that you can use on different data sets. This is an example of causal representation learning. I've mentioned this before, but the basic idea is that you start with data on the pixel level and you want to learn an encoder from the pixels to a smaller number of causal variables. And you also want to learn some kind of causal structure, some SCM or other causal model between these high-level variables. Now, we're not the first to look into causal representation learning. And many people have tried to understand the question, under which circumstances it's possible to do this, learn the right causal variables and learn the right causal structure. And whether this is possible generally depends on two things. It depends on what whether you turn on your laser pointer, what kind of data you have available. That's on the y-axis here. So do you just have unsupervised data that is observation, so no interventions occur, no actions are performed, you just record a system without interfering with it? Or do you have labels, or do you have something in between where maybe you have some kind of structure or weak supervision, but don't need actual labels? That's the one thing it depends on. The second thing it depends on are the assumptions you make on your model. So for instance, you could not assume anything. You could say there's some unknown causal structure between some causal variables. You could say we know at least the causal graph, but not the variables. You could say we know that all the variables are independent, or you could even say that we assume some things to be linear, some distributions to be non-Gaussian, and so on, which are really strong assumptions. And over the last 25 years, there have been lots of work that show that under some circumstances, it is possible to really find the true causal variables just from pixel-level data, starting with work on ICA that you may have heard of by Apo Kibarin and his collaborators in the 2000s, and going all the way to work, for instance, by your fellow student, Philip Lippe, that some of you may know maybe from some lectures, that Sarah was also involved with, and many works in between. I will not go into details on this, but lots of great work. At the same time, some people have shown that in many cases, if we have no strong model assumptions and no labels on our data, it's actually impossible. We can just as well find a like kind of wrong mapping of pixels to causal variables. So some totally bullshit description of a system, but it's still totally compatible with the data. And there's no way of telling a wrong description of the data from a true description of the data, just from the data alone. For instance, Francesco Locatello won a best paper award at ICML for this insight, but there's many other ways. This divides the space of data settings and model assumptions into, yes, drum roll, two areas. There's the setting that we know as identifiable. So this is kind of model assumptions and data settings where it's possible to learn the right causal variables just from data, at least in theory. And then there's the setting of non-identifiability where we can't ever find out the right causal structure unless we get lucky. But these two regions don't yet match up. There's a lot of settings that are unknown where that's possible to learn the causal variables. And our work that I'm talking about now tries to fill this gap a little bit and succeeds in that. And showed that it is possible to learn causal structure if we don't make any assumption or almost no assumptions on the model with some form of weak supervision. Okay, this was a lot of details. Maybe, again, squinting a little bit. I think one message that you should take away from this, if you care about this causality stuff, is it is impossible to learn causal variables in structure just from observational data unless you make strong assumptions about a model. It is, however, possible to learn things like what are the important high-level variables, what is the causal structure between them. If you have non-IID data, if there's some change in the system, and maybe to say this in a kind of polemic way, maybe if causality is the language of change, then change lets us identify causality. Now, this is kind of a nice statement if you look from really far away. If you get to the details, unfortunately, it gets a little bit more ugly. But if you want to take away one thing here, this may be it. Okay, now, I have time to go a little bit into our findings in the theory, but I will not really go through a proof or anything, but I will advertise the paper. So to show this, what I just said in a very high-level way, in theory, we need to make some definitions. And the first is that we introduce what we call a latent causal model, which is a number of high-level variables with a causal model in between them. So a structural causal model, this SCM consisting of mechanisms and noise variables. And then there is a decoder, a rendering function that maps these causal variables to some pixel space. So just a like a decoder and a VAE. Because we have this structural causal model in the latent space on the left side, we can reason about interventions between these variables. We can, for instance, ask if we change the value of one of these variables in an intervention, what happens. And because we have this decoder, we can observe what happens on the level of pixels. So if we have this domino system, we can kind of see the effect of the intervention in the pixel level space could look like going from dominoes standing upright to half of the dominoes having fallen. With this formalism, with this latent causal model and its abilities, we can make the assumption that in some settings, we can observe data generated with some ground truth latent causal model through interventions. So we want to observe a system, or we consider the case we observe a system before and after something changes. So think of a traffic intersection, car standing at a red light, and then we kind of flip the traffic light state to green, and we see how take another picture of the system a few minutes later, and we see the cars now driving. So we only observe the system on this pixel level. We only observe the picture of the red traffic light and cars standing, and then the picture of the green traffic light and cars driving. But this is the data setting that we are interested in, and we assume that this data was kind of secretly generated from a causal model in some particular way. No further labels. Assuming we have this kind of data, we can now consider the case where we fit a neural causal model, kind of a same structure. So we have a latent model, we have a decoder, and we fit this to the data, to the pixel level before, after pairs. And what we show in theory is that if you do everything right and really find the global minimum of your loss surface, that the model that we fit to this before-after data and the unknown ground truth causal structure of the world will be exactly the same. They will have the same causal variables, they will have the same causal structure, and they will have the same mapping to pixels, up to some small ambiguities. For instance, the variables could be reordered. There's no way of knowing which one is variable 1, 2, and 3 in each model. They could be ordered as 2, 1, 3 in the second model. So this is really the theoretical insight. And again, to say this on a really high level, we show that from changes that correspond to these interventions in a latent space, you can identify causal structure. Now, I don't want to talk about the proof, but if you like math and string diagrams, I do encourage you to read our appendix of the paper. But what I do want to say is that there's no free lunch, and there's unfortunately a lot of assumptions we need to make to write this theorem. And for some of these assumptions, they also mean that it's kind of really hard to apply this to real-world systems out of the box. And there's some progress in relaxing this, but it's still, there's a lot of work to be done here. And to give you one example, right now, we assume that each causal variable is just a single real number. So our method doesn't support causal variables that are, I don't know, higher dimensional vectors or discrete variables or something like that. Yeah? This is for the causal variables, like the high-level variables, the concepts like the velocity of the car. The pixels, they can be just whatever. They can be RGB pixels, or you could even have point clouds or any observation space. There's just a little bit, in the theory, there's some kind of smoothness assumption in the map from causal variables to pixels. But in practice, I don't think you even need that. Anyway, of course, I don't want to talk about the weaknesses of our result, but it should always be important to keep in mind that theory results in machine learning are often quite far away from applicable setting, and this is yet another example of that. Maybe even worse than some other results. But now, if you want to use this in practice, you should, we found a way of doing this. It may not be the only way, but maybe the way we like the most is in a variational autoencoder. So you build a neural network model that consists of a map from the pixel level data to some latent space. Let's call this an encoder. There's another map from the pixel level space to, from the latent space to the pixel level space again, a decoder. And then there is a probability distribution over the latent level, some prior. And it is the job of the prior, this distribution over these causal variables, over these variables, to describe the causal structure in here. In the beginning, when I talked about this framework, this structural causal models, I said that structural causal models allow you to get probability distributions, both for observational data and for interventional data. And this is exactly the ability that we use here. If we have a structural causal model over the variables in the latent space, we can use this to get probability distributions before and after the intervention. And maybe this is the level of detail where I will stop right here and not really talk about details in the interest of time. But a lot of the work in a project like this is actually getting this to work in the actual implementation. Now, what can you do with such a model? You train it on pairs of data, on these kind of before and after images. And after you've trained it and make sure that your model didn't get a NAND, the loss of the second epoch, and actually converged and all of this, you can use it to, and most obvious thing is you take images as input and map them to causal variables. You can look at the graph that the model learned between the causal variables and just then, interesting, the traffic light causes cars to change their velocity and not the other way around. You can also use this as a model that detects what happened in the before-after image, so you can kind of infer the actions or interventions between two images. And finally, it's a generative model like any VAE, so you can generate observational or interventional data. You can use it to reason causally, as I'll show you in a second. We demonstrate this on some data sets. Some of these data sets are kind of boring benchmark data sets, but we also created our own. We called it CausalCircuit. And it's exactly this animation that I showed you before. So you have a robotic finger interacting with a system of connected buttons and lights. And there's this somewhat silly toy graph here. So the robot arm position always causes the state of these lights by touching the buttons. But we also, to make it a little bit more interesting, we added this effect that when the blue light goes on or the green light goes on, the red light is kind of like a summary light that always goes on with them to make it a little bit more interesting to learn. And then we trained this model just on pixel level data, not on videos, but on just pairs of images.
You discovered this called the Latent graph. Can you use that when you have further data in a continual manner to like update it, add new variables?
It should in principle be possible somehow, but it's a difficult question to figure out how. So we didn't do that. I think that there's some work here at UVA where people think about this, maybe not exactly in the way that you described, but more in the kind of the scene composition is variable. So sometimes you may have more or less objects in each scene, but that is already quite a difficult setting, even if you have all possible combinations in your training data, and we didn't think about this. This goes a little bit in the direction of object-centric learning, but they usually don't have a causal graph. So I think like a project that does something like object-centric learning, where you learn something like a kind of variable number of item mechanism that assigns pixels to slots or something like that, and then also learns like a causal graph between the slots, that would be super cool. And I haven't seen a really convincing paper or like any paper really of this yet. Yeah?
So follow-up question. So in this paper, you assume you know how many causal variables there are?
In the theory, we don't. In practice, we do.
Right.
We didn't check. We should have checked, but we didn't check what happens if you just always put this number to 16 or something, and then in practice just have 4 variables. If it then learns that some variables don't matter with some regularization. Yeah.
Is there limits on this graph, or can there be multiple solutions to the problem?
We make one assumption that's often known as faithfulness, which kind of means that each causal graph error that exists in the causal graph also has to have like a visible impact on the distributions. They can be not kind of vacuous errors. Like if I draw an arrow in the causal graph, it means that I must be able to measure its effect. Otherwise, I could just drop the arrow. And under this assumption, the causal graph is indeed unique from the data. So you will recover exactly the right causal graph. So in this particular example, what we do find is, okay, first, do we learn the right causal variables? What I show you here is an embedding of one image, and then kind of we take the latent space of our model and just vary one factor and keep all the others fixed, right? And you see if we just vary one latent variable for model, Z1, the only thing that changes here, it's a little bit hard to see, but it's the position of the robot arm. Yeah, and you get the images by kind of varying the latent factor and pushing it through the decoder again to the pixel space. If we just vary Z2, everything stays in place. The robot arm doesn't move. The 2 other buttons don't change, but the red light goes on. It's also, yeah, this is a little bit of an eyesight test for you. Z3 corresponds to just changing the green light, and Z4 to just changing the blue light. So the latent variable learned by our model really are in one-to-one correspondence with the ground truth factors of the system, which is the robot position and the 3 light states. Now, second question, what about the causal graph? So I showed you this true causal graph already. And what our model learns, maybe if you just see it at first, in the same ordering that the model learned, it looks a little bit different. The ordering of the variables is in some other way. But if you kind of mentally move these things around, you see that it's exactly the same graph. Or technically, the 2 graphs are isomorphic to each other. It correctly inferred that the robot arm causes all the other variables to change their state, and that the green light and the blue light cause the red light to go on as well. And then finally, because we have this causal model in the latent space, we can use our model to reason causally. We can, for instance, take an image, encode it into a causal model, and then ask the question, what would happen if? What would happen if we move the robot arm somewhere else, including all causal effects? And let's see if this is visible. If you move the robot arm and then kind of in this movement, it would touch buttons, our model imagines correctly how these lights would light up. So that's nice. Causal models do allow you to do this kind of answering what if questions, or maybe doing something like planning with that. Like now you could figure out what you need to intervene on to make the blue light light up and so on. But to not get too excited, I think this was a nice proof of concept, but causal representation learning is really quite far away from being applicable to real world problems right now. So many of the papers, including ours, do things like theory on identifiability, asking the question, under which theoretical assumptions can you really uniquely, correctly identify causal variables in causal structure? And that's great. But what we really ideally want is some downstream problem like planning, or I don't know, solving cancer, that you can really solve better if you use these kind of models. In this particular paper, we use this pairing of pre and post intervention data, but this is really an unrealistic abstraction away from the data that we can observe in reality, something like the pixels of a video feed. And there's some way of translating one setting to the other. We also didn't really talk about how to perform interventions. So ideally, you want to kind of learn this as well. And then one thing you asked about a second ago is this question of, we fix the scene composition right now, but ideally you'd have this variable and be different for each data point and maybe add more things later on, and so on. So maybe to summarize this, right now we have the stage of toy experiments in this field, and we are far away from real world experiments. That being, okay, one typo for one question, but do ask it.
Okay, the question was regarding the does that go in the direction that if an agent does an action that basically knows that action, so he knows the intervention?
Yes.
Which, yeah, the easy way to get interventions in a natural setting.
Yes, that goes exactly in that way. And we'll also talk a little bit about something like that next. So, yeah. Okay, maybe to wrap up this part, there's some progress recently, not just, well, a tiny bit from us, a lot from other great people on the question, is it possible to learn causal variables and causal structure from pixel level data? we looked at this particular case where we don't have labels, but we have non-IID data. We observe a system before and after something is changed in the system. And we showed that that is enough. This kind of change, observing change, is enough to identify causality. And we can, on toy problems in a simplified setting, we can make this work with a particular form of VAEs that we introduce. If you find this more interesting, I love all the questions, but I do want to point you to this resource that, so I can get into the next topic as well today a little bit. It's this paper from NeurIPS last year with my co-first author, Pim Dahan, Philip Lipper was involved, and Tucker Cohen. And I also put a few other references on the slide on other great works in the space. So much has come up this year that I didn't really have space to add more papers, but it's a really dynamic area of research right now. And of course, you have Sarah here as a professor. You have Philip here as a, I'm not actually sure, but I think he's supervising thesis as well. So you're in great company if you want to work in this space. And I think this kind of, there's many things to make progress on because it's still a very unsolved problem. And if maybe you can solve some of these steps, it would be fantastic. Okay. Any questions before I go to the last part of the causality talk, where I talk about causality for machine learning? Excellent. Then let me jump straight in there. Imitation learning is, I assume, something you've heard of before, but think about autonomous driving. We don't really want to solve autonomous driving by doing reinforcement learning on real roads, I think. And have you seen bikes in Amsterdam? Anyway, so maybe the best way of solving this is putting a human expert in a car, putting cameras on the car and recording all the action that the human does, and just storing trajectories of observations of then the actions like steering the wheel or hitting the brakes and so on, and making big data sets, and then using this to train a policy, for instance, with behavioral cloning, and deploying it on an autonomous vehicle. Now, what's the problem with this? Does anybody see the fundamental issue with imitation learning done in this way? Mm-hmm. That is a problem, and knowing how I drive myself, I think that's a pretty terrible prospect, but that's not the one I was hoping for. Mm-hmm.
That you're blindly following the imitation without causality.
Why is that a problem? That is indeed one of the problems of imitation learning, and I have a slide on that. So kind of, if your policy isn't perfect, you're always like, even if you have infinite training data, or not infinite, if you have lots of data in there, many situations covered, but if you kind of deviate a little bit from a perfect driver, maybe you steer right a little bit too late in a curve, you kind of arrive in unknown situations that weren't there in the training data exactly. And these small errors accumulate, and suddenly you are somewhere in a totally new situation, and your policy has no idea what to do because it was never trained on this situation. This has been known for some time, this problem. There are some attempts at solving this. For instance, you may have heard of the Dagger algorithm. But the good thing is that this problem should, in principle, go away if you collect loads and loads of data, if you collect infinite data, say, and you really have a good learning algorithm. So it's still a practical problem, and it's maybe a really important practical problem. But as a researcher that doesn't actually have to implement this on a car, I can say, easy, just get more data. It will solve itself. There's another problem. Any more takers? Okay, I have to spill it. When you put a human in the car to get demonstrations, the human doesn't just have exactly the same observations that the agent will have later. Instead, for instance, the human in the morning listens maybe to the weather forecast, or maybe talks to his friends and hears something about the situation on the roads. Or maybe also in the car, the human has ears. The human hears there's an ambulance approaching from the side, from the sirens, but the car later only has a camera. So there's a mismatch between the inputs. And why is this a problem? The expert actions will depend on this additional input that later the agent will not have. So for instance, if you hear a siren approaching, and even if everything looks good, you may kind of drive very cautiously, maybe drive a little bit to the side to make room for whatever's happening and be more attentive. If you don't hear a siren approaching, you just go straight ahead. at maximum speed. When you now deploy an agent and train it on this kind of data, there's no way of knowing, just seeing the road and nothing being weird, if you should go slow or fast. So there's no principled way for the agent to make these decisions. So the behavior coding algorithm just tell you pick one of these two speeds at random. And it gets even worse. If you train an agent on data like this, one pattern that the expert will have is that kind of when you drive fast, you're more likely to drive fast in the next time step as well, and so on. So kind of there's a correlation between your past behavior and your next behavior. When you drive slow because there's an ambulance coming, it's also more likely that you keep driving slow until the situation is resolved. So if the imitator kind of initially decides to go fast based on the sensory inputs it has, and then it knows that the patterns in the data is if you go fast, you continue going fast, it will kind of continue this pattern as well. It's known as causal delusion. So you take your own past action as the imitator as evidence to base future actions on, even though the past action was kind of ill-informed and not actually based on the same input that the expert had. So this feels maybe a little bit construed, and we're still in the process of figuring out how widespread this problem is actually in real life autonomous driving situations. But this is definitely a problem that doesn't go away with infinite data. If you have this information asymmetry between the expert and the imitator, you have a problem, and this problem may even get worse when you train more. You can look at this problem with a causal perspective to gain some insight into this. So the causal graph of an expert interacting with the system looks a little bit like this. So you have some observation S, you have some additional information, which is like the sound of the siren, or maybe the weather forecast in the morning that tells you that the road is icy or something like this that the imitator later won't have. And both the observation, the camera feed, and this additional information will influence your action. And then the next observation will depend on a mixture of these things as well. It will depend on the extra information, because if the road is icy, for instance, then the road will react differently. If there's an ambulance coming, then other cars will react differently. And it depends on the action and on the last state, of course. For the imitator, the situation is similar, except that the action now cannot depend on this extra information. The transition dynamic still depends on it. So the road conditions or the presence of an ambulance or something still affect how the environment changes, but the action cannot be informed from this theta. And if you look at this framework of causality, you can see that these two situations can be described in one joint causal model, where the difference between these two distributions is exactly an intervention on the mechanism that generates the action. So causality has a framework to talk about the situation. Now, I do want to give you your lunch break, so let me kind of rush through this a little bit. But using this knowledge of the causal structure of the problem, we can kind of derive the policy that an imitator uses when they kind of naively follow the expert data, just minimize the distance to the expert data. It has some equation. It's we call this a conditional policy. It's kind of wrong. It will make mistakes. And then there is this interventional policy, which is the thing that you'd correctly do if you'd account for this intervention between the observed and the acted data setting. And then we do some theoretical analysis of this, but also skipping over this. The most important thing is that you could then construct a practical algorithm that basically learns an encoder that takes the observed data that you kind of encounter on the road and maps this to some belief over latent variables. That's the first component, together with the second component, which is a policy that takes the current state, the belief over latent variables, and then decides what to do next. And we show in theory and practice that if you do this in the right way, if you update your belief and then act under the belief and then update the belief and then act under the belief, you can correctly learn this right policy that is not affected by this information mismatch, or at least initially you're still affected, but then during the course of your rollout, you learn more about the stuff that you don't know. Yeah, I think I just want to show you one plot of this. So we did experiments, for instance, this LunarLander environment that maybe you know. This is one of these Atari video games. Is it Atari? I'm not sure. It's an old video game anyway. And it's one of the environments that used to be in OpenAI gym back in the day. And we make this random by saying that the way that the keys on your gamepad correspond to the actual actions that the computer performs is randomized. There's some unknown reshuffling of the keys, maybe Yeah, it's a little bit toy, but it has the same effect as some unknown latent. The expert knows which key does what, but the agent does not. And then we try to train the agent on expert data. And what we find is that if you do things naively, so here you have training progress on the x-axis and rewards on the y-axis, you see that an oracle, which is the same as the expert, this black line, gets a kind of high reward, and naive behavior cloning, just the standard algorithm for imitation learning, gets a pretty shitty reward here. And our algorithm starts out pretty bad as well, but then ultimately learns to get reasonably close to what the oracle is doing. And this gap is kind of remaining from the beginning of the episode, where you first have to do some actions and figure out what actually the right key binding is. But then after a certain point, you can see that the agent really learns to correctly infer how to act from past actions. It kind of learns to probe its environment to figure out the stuff it doesn't know. So to just wrap up this part, apologies for going really fast and not talking about the math behind anything, but in imitation learning, we often have these information asymmetries that the expert and the imitator don't have exactly the same information. And standard imitation learning will then fail. It may fail just a little bit, such that it doesn't matter, or it may fail really badly, such that the algorithm does something catastrophic. And we can improve the situation, and we're not the first to realize this, but we kind of contribute to this a little bit. We can improve the situation by analyzing the expert situation and the imitator situation causally, and realizing that they really differ through intervention in a certain sense, and then identifying the right way of constructing the policy, and that gives us an algorithm that we can use in practice. And if you actually want to understand this stuff in a little bit more detail, I'd encourage you to have a look at this paper, Deconfounded Imitation Learning. This is an example of a work led by an intern working with us, Risto Fuorio, at Oxford now again, and my colleague, Pim Dahan. There's also 2 other papers that one by 50 authors, and from this you may already guess where the authors work. Yep, DeepMind. And another one by some folks, I forgot where they are, that study the same problem and come to slightly different solutions. But it all has different strengths and benefits. So to wrap up, what I wanted to talk about in causality. Causality is, from a distance, if you squint a little bit, a framework that lets you talk about changing conditions. And maybe this explains a little bit why Qualcomm cares about this. We sometimes do research that's more on the long-term horizon, has potential to solve big problem side. This is an example of that. And we believe that causality may be a piece of the puzzle to really make things more robust to changing conditions down the road. Maybe in autonomous driving, maybe in robotics. But that's our vision for causality. The work that we have right now is quite far away from being applicable to a real autonomous vehicle or anything like that. But I think we're making some conceptual progress, both on the side of machine learning for causality, learning the causal model of the world with deep learning, and on the side of causality for machine learning, how we can use a causal perspective on a learning problem to make problems go away that even infinite data, that even scale can't solve. This is all I wanted to say. I wrap it up now, but feel free to ask me questions after that. We'll take a lunch break now, and my colleague Thies back there, and then later my other colleague Jens will continue talking about compression at 1 in this room. Thank you very much.